let's try another application of expected utility theory, this time to the topic of securitization. So what do we mean by this? Well, let me illustrate it just with the following kind of context. The question is, what does a risk-averse person need to be compensated to bear risk? Now to see this, let's think about, suppose there's an investment opportunity. With 60% probability, a $100 investment today will yield a payoff of $200. But with a 40% probability, it yields nothing. Okay? What's the expected value of this thing? Well, you pay out 100 with certainty to go into this deal. 40% of the time you get back 0. 60% of the time you get back 200. So if we add up these probability weighted things, well, with certainty we lose 100. With 40% probability we get back 0. And with 60% probability we get back 200. 60% times 200 is 120. So minus 100 plus 120 is 20. In other words, this thing has positive expected value. The expected payback of 120 is bigger than the upfront cost of 100. If not for risk aversion, this one's a winner. Now in this class, we don't worry about the time value of money, so you could just think about these dollars all occurring at the same time. So this looks like a winner, again, if not for risk aversion. Now let's put this into our little framework and think about the possible wealth outcomes with the big investment. We need some assumption about initial wealth. Let's suppose the initial wealth is 100. So this person has two decisions. This person can invest or not invest. And either the good outcome can occur or the bad outcome. If the person doesn't invest, the person has their initial wealth of 100 either way. If the person does invest, they put in 100, 40% of the time they get back nothing, 60% of the time they get back 200. So those are the four possibilities. Really two possibilities per choice, where invest and not invest or don't invest are the choices. And so the question is, does a person who's risk averse and whose attitudes towards risk are described by our, U equals square root of W utility function, does this person undertake this investment? Now, to analyze this, what we need to do is compare the utility of that initial wealth, that 100 with certainty, and that's not an expected utility, it's just a utility. We'll compare that to the expected utility if the person were to take the risk. So what are we doing? We're literally comparing U of 100, which is square root of 100, versus the expected utility of taking the investment, which is what? Well, it's 0.4 times the utility of my wealth if the investment fails, plus 0.6, and this should be a times, times the utility of my wealth if it succeeds. In numbers, that boils down to this. The square root of 100 is 10, so that's my utility if I don't invest. My expected utility if I do invest is this thing over here, 0.4 times 0 to the 0.5, and of course that's all just 0, plus 0.6 times 200 to the 0.5. That's just 0.6 times the square root of 200. So down on the next line, we take it a step further. It's 10, which again is the utility of not investing, versus 0.6 times this 14.14215, and that all equals 8.485. The key here, of course, is that 10 is bigger than 8.485. So the investor, characterized by this utility function, passes on this opportunity, even though it had positive expected value. So it would, in some sense, be good for society to have done this. So it's too risky for this individual, and as a result, society lives in caves for a few millennia. What I mean by that, it's a little bit of a joke, but it's a little bit serious. The idea is, without some ability to share risk across people, we don't undertake investments, and so we don't develop. And so there's that cave and the dude who lives in one. Okay. Now here's the innovation. What if we were to break this investment into chunks? Let's even call them shares. Maybe you see where we're headed here, but let's call them shares. So these shares now are going to be priced at 10, and instead of one investment costing 100, we'll have 10 investments or 10 shares each priced at 10. You'll see that the sum of these shares collectively has the same properties as the overall investment, but we're going to be thinking about the investor's attitude toward one of these shares. So again, what does a share do? Well, it returns $0 with probability 0.4, and it returns 20 with probability 0.6. So it's just 1/10 of the payoff of the overall investment we were just thinking about. What's the expected value of one of these shares? Well, it costs 10 with certainty, pays back 0 with probability 0.4. It pays back 20 with probability 0.6, and so minus 10 plus 12 is 2, so it's got positive expected value. Let's also translate this into the possible wealth outcomes for the individual, depending on whether he or she invests or doesn't invest. We also need to specify an initial wealth. Let's say the initial wealth for the individual is 100, which is the same as it was before. So now, what are the possibilities? Well, now, if the person invests and the good outcome occurs, the person has 110 because they paid out 10, got back 20, so they go 100 minus 10 plus 20, and that's 110. The bad outcome occurs, they pay out 10 and get nothing back, so they have 90. If they don't invest, of course, they have 100 either way. The game plan here is to compare the utility from not investing to the expected utility from investing. So let's do that. Whoops. So let's compare the utility of not investing. This W0 is the initial wealth, which is 100. Let's compare that to the expected utility for each investor. So over here we have the utility of 100, square root of 100. Over here we have 0.4 times now 90 to the 0.5. What's that? That's wealth in the bad state. I started with 100, I put in 10, I got back nothing. So I have 90. We raise that to the 0.5 plus 0.6, the probability of the good outcome, times my wealth, the utility of my wealth in the good outcome, which is 110 raised to the 0.5. Plugging some things in here, using a calculator for sure, we have 10 over here, the square root of 100, and that's just, again, the utility of not investing. Over here, the expected utility of investing is the 0.4 times 9.4868 plus 0.6 times 10.4880, and that all equals 10.087. The key here, what's punchline, drum roll, etc., is that 10.087, the expected utility of investing, is bigger than the 10, which is the utility of not investing. So this individual invests. This is so cool. We have 10 individuals who take this deal. This investment occurs, and so we can move our way out of caves. And literally, this is an idea that launched 1,000 ships. The Dutch East India Company is often credited with this idea, breaking investments into shares and allowing more people to invest, put less at risk, and it allowed a lot of capital accumulation and a lot of, in this case, the real investment was buying ships that then sailed around to bring spices from the East Indies and so forth back to Europe. Quite risky endeavor, especially for the sailors. But from this perspective, we're worried about the investors, although as a human, I'd worry more about the sailors. Okay. So, takeaways. This video was about an application of expected utility theory, so we didn't actually learn any new concepts here about the expected utility model, but this is a really important application, so let's just talk a little bit about what made it go. So it's the dislike of risk in the first place that makes investment, or just in general, that makes risk-bearing difficult. Investment being one kind of risk-bearing. And the key insight here of the Dutch and in our module today is that breaking risky projects into shares, which is what we call securitization, makes it possible for society to undertake big projects through financial markets. The word financial market innovation has acquired kind of a negative tone or overtone after the financial crisis, but there was a time when financial market innovation, like this one, was quite a good thing, unambiguously.